Got a full can of beverage.
Yeah.
Its center of mass is in the middle.
Yeah.
As you drink the beverage and it gets lower, the center of mass moves down. But then once the can's empty, the center of mass is back at the middle again.
Yeah.
And the question is, what's the lowest point the center of mass reaches in a can?
Yeah.
Hello, welcome to my first programming exercise video. I saw this discussion and I thought it sounded like an interesting problem because the solution wasn't immediately apparent to me when I heard it, and it also seems like it was difficult enough that I could quickly throw together some math and program at it to visualize. So I thought I'd give it an attempt, starting with a discussion of what a center of mass is. I call a center of mass a weighted average. So for this one-dimensional example, we have some blue circles or masses separated from some center point at 0, and the heavier the mass, the more they will tend the average separation from the center towards their location. And we end up with a equation that is the sum of the products of their separation in masses normalized over the masses. For this example, we get 0.25, slightly towards the right of the center. I think this makes sense intuitively because our left and right endpoints are equidistant and equal mass, essentially canceling themselves out if we imagine them as children on a seesaw. And the equidistance 3 and 1 tends favorably towards the 3, bringing us slightly towards the right of center. But summing over points doesn't quite make sense for our example where we're concerned with a cup and water in it. So we have to transform our discrete summations into continuous integrals where we're now integrating to find the sum over infinitely small pieces of volume. And we get an equation like this where we're integrating the separation z times now the density over volume gives us the total mass like before. I've represented our question using this picture here, where our cup has a rim at the bottom from height 0 to h1, and a total wall from h1 to h2 with a thin ring of radius r1 to r2, and will represent the height of our water as some w as a function of time. For the x and y directions, the center of mass cancels via symmetry and hence is the center of our cup. And therefore, we're primarily interested in finding the center of mass as a height of our cup. So we'll integrate over 3 parts of the volume. First is this rim I call the base at the bottom, and then the rims that are the stalk of the cup I call the walls. And finally, the volume of the water, where we have a rho g, the density of the glass, and rho w, the density of the water. The numerator and denominator are different via this equation by putting in our separation from the 0 over axis inside of the integral. To calculate this integral over volume, we're going to use polar integration since we're basically finding the volume of a cylinder. The small slices of area in polar coordinates is approximately a rectangle in this picture, where the length and width of our rectangle are some dr, and arc length, which is the product r d theta. And we'll use this as our differential on our integral, and of course integrating over height as well, where we're basically stacking circles and multiplying by the height. Okay, so this is our equation now, where we've separated our height, radius, and angular terms for the 3 pieces of volume we want to integrate over: the base, the walls, and the water. The base goes from 0 to h1 and 0 to r2. The walls go from h1 to h2 and from r1 to r2, and the water goes from h1 to w and 0 to r1. The only difference between the numerator and the denominator is that our height has this z term inside of the integration. So using our integration knowledge, we'll just compute and simplify using some algebra to get an equation like this. Moving to my program, I'm using Google Colab and coding in Python. So ignoring my import statements, I first began by measuring this cup with a ruler and getting the dimensions here. And a quick Google search tells me the ratio of density of glass and water. And we're going to use a time between 0 and 1 to show that our cup has the water emptying. It doesn't quite matter that we're doing it in a line, it just helps us understand the value of our center of mass as a function of time more clearly. So we're going to drain our cup. We'll calculate the center of mass z using the equations we found in math, plugging in w of t, making a call to our function that we've defined being height. And if we plot these, we get a result that looks like this. And here's the plot we get for the center of mass. And it makes sense because our water containing mass brings our center of mass towards the center, and as it's drained, it brings the center of mass down with it. However, at a certain point, the rim of the glass contains more mass than the water at the bottom of our cup, and so we start moving upwards again. We're writing some code to make a visualization, and we can have something that looks like this. If you want to check out this code, I'll put a link to a GitHub gist, so you can mess with the dimensions of the cup and the densities of the glass and liquid.